All right, let's look at the differential equation problem number 18. All right, it says this: suppose that f of x comma 0 equals 0, and a partial derivative of f with respect to y at x comma 0 does not exist for all x, which is a real number, and is y identically equal to 0, a singular solution of the initial value problem y prime equals f of x comma y, and y of a is equal to 0. All right, let's just first check that y equals 0 is a solution of the given initial value problem. All right, so y equals 0. So here y of x is identically equal to 0. All right, let's check the differential equation. So the differential equation we need to satisfy would be y prime is equal to f of x comma y, right? All right, so obviously if you take the derivative, so y prime is going to be 0, right? So the left-hand side is going to be 0. Then since y equals 0, right-hand side is going to be f of x comma 0, and which is actually given right here, that it's going to be 0, right? So you can see that if y equals 0, left-hand side and the right-hand side of the differential equation are both 0. So we know that it satisfies this differential equation, at least. And the initial condition, f of a must be equal to 0. This is kind of trivially satisfied because y is 0 all the time. So we know that we have initial condition is satisfied. So therefore, right, y identically equal to 0 is a solution, right? All right, then we want to see if this can be a singular solution. So a singular solution is a solution that cannot be a part of, that's not part of the general solution, you know, the one with the C in it. All right, and so if the initial value problem has a unique solution, then we should be able to the solution cannot be a singular solution because it's going to be a part of the general solution. So if you have a initial value, then you should be able to identify a unique solution. All right, let's look at this theorem, existence and the uniqueness of the solution. It says that suppose that the function f of x xy and its partial derivative, so here this is the partial derivative, and the requirement is it has to be continuous, and the given problem here, we have a little problem here. All right, oops, this says that the partial derivative f with respect to y actually does not exist. All right, so with that condition, it does not satisfy the hypotheses of uniqueness and existence theorem. So it's not guaranteed that we're going to have a unique solution for this initial value problem. All right, so let's see if we can come up with an example where y equals 0 is actually a singular solution. All right. Here's the example. All right, you have dy over dx is equal to 6x y to the 2/3 power. All right, then initial value. Oh, I forgot to add the initial value. So that's the differential equation, and then y of a, say, is equal to 0. Actually, maybe I'll do a y of 0. Let's make it as concrete as possible. So y equals 0 is 0. How about that? All right, and then what we want to do is, let's see, we want to try to solve this differential equation. And here we get take the this is a separable equation, so I'm gonna go down here. All right, I guess I'm going to first divide through by I'm gonna actually 3y 2/3 power. So we're gonna get let's see, dividing by 3, so 1/3, dividing by y to the 2/3, so it's gonna y to the negative 2/3, and you have a dy over dx, and right hand side is going to be 2x left over, right? Then we take the antiderivative of both sides with respect to x, so we have that. Then we can cancel, all right, dx here and dx is gone. All right, antiderivative is going to be, all right, 1/3 is sitting right there, and add 1 to the power, so you have a y to the 1/3 power, then divide by 1/3, right, is equal to antiderivative of 2x would be x squared, right, plus some constants c, right? So we have that. Then we can cancel, there's 1/3 on top and 1/3 on the bottom, and we can, let's see, we can just cube both sides. Then we can just isolate y. So we found a general solution, which is quantity x squared plus c cubed, right? So if you want the initial value problem, so we can just try y of 0 is equal to, we have 0 squared plus c is going to be just a c cubed, and we want that to be 0, and which means that the c is equal to 0 anyway. All right, so therefore the particular solution is y is equal to x squared cubed would be x to the 6th power, right? So that's the solution, right? But as it turns out, this is not a unique solution. There's going to be a singular solution which is not part of this, the general solution. All right, so that is y identical equal to 0. Right? You can see that y is equal to 0 satisfy this inequality. The differential equation, because if you compute the left-hand side, derivative of y with respect to x is obviously 0 because it's a constant 0. Right? Then if you compute the 6x, you have a 6x, and y is actually 0 raised to the 2/3 power is a long way of writing just a 0. Right? So the differential equation is satisfied, and obviously f equals 0 satisfied. So we have a solution which is actually does not come from the general solution. So you have a y equals 0 is a singular solution, right? And in this example, if you take the partial derivative with respect to y, so let's try that. So this is our right here, this guy is our f of x comma y, and let's take the partial derivative of this f with respect to y. Right, so then you're going to get, right, 6x is just going to be a constant, so put that there. And a partial derivative of y to the 2/3 power. So we put the 2/3 in front, and y, and subtract 1 from the power, so it's negative 1/3. Right? Then we can cancel 3 and 6, so that's 2. So we end up getting, let's see, 4 x over, right, cube root is the negative power of y. All right, so you can see that when, let's see, y is equal to 0, when you look at the partial derivative of f with respect to y at x comma 0. And you can see that you're going to get the 4x over cube root of 0. This guy is actually undefined. Does not exist. Maybe I should say does not exist, because that's what they said here on the problem. So does not exist. So it fits the property here. All right. So as you can see in this example, y identical equal to 0 is a singular solution, because this does not come from the general solution we get by solving the differential equation. All right, so let's try to visualize what's going on here, right? So let's look at the slope field of this differential equation, right? So I pull out the GeoGebra, and I'm going to just type in slope field, so here. All right, so the equation was dy over dx is equal to 6x times y to the 2/3 power, right? So it looks like that. So I'm going to just move it over here and maybe stretch it out. All right, so one of the solution was y equals x to the 6th power, right? Which looks like this, right? And that go through the origin, so it satisfied the y0 equals 0 initial value condition. And another one, you can see that, so this was a solution, and y equals 0, as you can see, is also a solution. Oh, sorry, I erased the other one. Y equals x to the 6th, right? All right, maybe I'll stretch it out a little bit here, and maybe here. All right, so you can see that here, this is the red one is y equals x to the 6th power. It goes along with the slope field, so it makes sense that this was the solution. And another one, if you look at the flow along the x-axis, y equals 0, it actually around the x-axis, you can see the flow becomes completely horizontal. So you can see that even though it has exactly the same initial value, that means that it goes through the 0, 0 in this case, still we have two separate solutions, right? So if it's if the initial value problem has a unique solution, there should be only one solution curve going through the origin in this case. But since it does not satisfy the hypothesis of uniqueness existence theorem, this is a good example where initial value problem does not have a unique solution. We have actually multiple solutions, right? And the y equals 0 is going to be a singular solution because this is not a part of a general solution we get by solving the differential equation. All right, then another family of solution, we can kind of play around with it. Say you have x squared minus, say, 2 and cubed. This is going to be another solution. It's kind of a funky looking solution curve here. All right, so this guy is another solution, and maybe we can just make it a little bit smaller so you can see the curve a little bit better. All right, so the blue curve is another solution with a different initial value, of course, but you can see that this guy follows the slope field very, very well, and this is the another solution that comes from the general solution with a different initial value. All right, but anyway, the point is, so go back to the problem. And so if you have a case where f of x comma 0 equals 0, and the partial derivative with respect to y does not exist, and you could have an example where y equals 0 is a singular solution, right, which does not come from the general solution that we get from solving the differential equation. Right? That's it. I hope that this was clear.